Hello everyone. Today I'm going to be discussing Vitali sets. So this is again a bit of lecture, a bit of measure theory that I'm going to show. So what are Vitali sets? They are non-Lebesgue measurable sets. Okay, and in the last lecture we showed that there do exist uh, Lebesgue measurable uncountable sets of measure zero. Okay, but you may be wondering, well, I can't think of a single non-Lebesgue measurable set. I mean, everything I can think of is measurable. Do there even exist such sets which are non-Lebesgue measurable? And I urge you now to pause the video and try and find one, but don't waste a lot of time because they're really hard to find. They do exist, but they're really hard to find. And in this video, I'm going to construct one. We're going to construct one and show that they do in fact exist. Now, it is in fact true that for the construction of a Vitali set, it's necessary to use the axiom of choice. So, axiom of choice necessary. So you can't construct a Vitali set without the axiom of choice. I'm going to be abbreviating this by AOC, necessary. I'm not sure if there's two C's here, but I think there are. So the axiom of choice is necessary. If you don't know what the axiom of choice says, then disregard this. But in the mathematics is built upon uh, axioms. It's an axiomatic system. That means the axioms are so sort of like base truths out of which everything else follows. And there's some debate about the axiom of choice and its validity. So if you don't know about it, just disregard this. But it's important to mention every time you're using the axiom of choice because some mathematicians don't think it should be a part of mathematics. If you're not familiar, just disregard it. But I'm gonna mention it just so for posterity's sake. Okay. And now let's construct this non-Lebesgue measurable set. Uh, okay, for anybody who is familiar with abstract algebra, group theory, you're gonna know what I'm doing here. So I'm gonna be basically uh, constructing the quotient uh, uh, group of real numbers quotiented by the rational numbers under addition. So this is what I'm going to be doing for the next uh, 5 minutes. So you can skip ahead if you're familiar with this. For everybody else, here we go. So consider the real numbers and consider an equivalence relation on the real numbers, which I'm going to define in the following way. X is equivalent to Y if and only if x minus y is an element of the rational numbers. Okay, one can easily verify this is an equivalence relation, and I'll leave that as an exercise for you. Uh, Now let's take a look at the equivalence classes of this equivalence relation. So equivalence classes are, as you know, I'm going to write this down. It's all the wise real numbers such that x is equivalent to y. So that's the equivalence class of x. And uh, it's important to note that equivalence classes require, representatives. So when I'm talking about the equivalence class of x, I'm in fact talking about this whole set. but it's represented by x. And it should be obvious to everybody who's ever seen equivalence relations that if, let's say, z is an element of this set, then the equivalence class of z is equal to the equivalence class of x. So basically, this set can be represented by any element of the set. So we can choose any element of the set to represent the equivalence class. And this is in fact an if and only if. So you can't have some z which is not in the equivalence class be a representative of that equivalence class. And now I'm going to write out what this means a bit further. Okay, so I'm going to basically write out the relation here. So y element r such that there exists some q such that, okay, q is obviously an element of the rational numbers, such that x minus y equals to q. So all the real numbers such that there exists a q such that x minus y is equal to that q, i.e. the difference is a rational number. Okay? And if you take a closer look at this set, basically what it says is that this set is the set of all x plus q where q is a rational number. And we can write this set just as x plus q. And in fact, I'm going to be using this notation interchangeably, so x plus q is going to be the equivalence class of x. So just so you know. Okay. And we know that equivalence relations partition their sets. So R is going to be a disjoint union of, now it's just going to be a union of x element R of x element R, x in R, the equivalence classes of x. But, uh, you know, take a breath here and think about how we can make this union a disjoint union. Well, in an equivalence relation, it partitions our set into smaller sets. And what should I replace here? What should I replace R with here so that this is a disjoint union? Well, instead of taking every possible x, I should just take an x out of every equivalence class. Okay? Out of every equivalence class. So the next step is use the axiom of choice to pick a representative of each equivalence class. Okay. Call the set of those representatives R. Okay. Now we've picked one representative from each equivalence class and we put it into R. So we're going to in fact have that the real numbers are a disjoint union of uh, equivalence classes represented by elements of R. So this is what we're going to have. And now we're going to do the following thing. we're going to do the following thing. Notice that for all x and for all x real numbers, there exists a q, a rational number, such that x minus q is an element of 0, 1. Now this is a trivial fact due to the density of the rational numbers. So let this be 0, 1, and let this be our element x. Can we find a q that's close enough to x such that when we take the difference, we end up here in 0 between 0 and 1. Of course there is, and this is due to the density of q. So even if x is an irrational number, we can still find a rational number that's close enough to x so that this happens. Okay, and now define P to be the set. Okay, for all x, let's denote this q by qx for each respective x. So let P be the set of x minus qx for all x in, not in the whole real numbers, but in R, in our set R, which we made. Okay, and you can see that x minus qx is an element of x. Okay, so in fact this means that x minus qx is the equivalence class represented by x minus qx is in fact uh, is in fact equal to the equivalence class represented by x. So we've basically translated our choice of representatives for each equivalence class from the general real line onto just the onto the interval between 0 and 1. So we have the following: P is between 0 and 1, and the real numbers are a disjoint union of x's P. Okay. Now this is a weird set. This is a weird set. P is weird. P is weird. So we looked at an equivalence relation on the real numbers, and we found a way to pick exactly one representative of each equivalence class such that all the representatives lie between 0 and 1. Okay? And now we're gonna suppose P is Lebesgue measurable. And just to note, I'm gonna be denoting the Lebesgue measure by m. Okay, and we're gonna suppose that P is Lebesgue measurable, and naturally we're gonna reach a contradiction. But exactly how is not clear yet. So let's have a look at that. Okay. So P is uh, a subset of 0, 1. Okay, and notice something. For all numbers z, and also we know that the real numbers are a disjoint union of x's and p and the equivalence class is induced by those x's. So for all real numbers z, there exists a unique uh, uh, x and p and a unique q such that z is equal to x plus q, such that z is equal to x plus q. Okay, how do we know this? Well, z is an element of the real numbers, hence it's somewhere in this disjoint union. So that means that there exists exactly one x such that z is an element of the equivalence class produced by x. Hence, there exists exactly one q such that z is equal to x plus q. Okay. Um, okay. And what if z is an element of 0, 1? What does that mean? If z is an element of 0, 1, what does that mean? Well, that means that our x is in 0, 1, since p is a subset of 0, 1. And furthermore, that implies that q is an element of somewhere between -1 and 1. Because if it's bigger than, if it's 2, for example, you choose x and your x is 0, then it's going to be 3 and z is going to lie outside of 0, 1. So this is the absolute boundary for q. Q has to belong to this set. Okay. Okay. And just now consider all the rational numbers that lie between -1 and 1. Okay. All such rational numbers. And actually consider this set. Okay, I'm just gonna consider this set. The union over all q's such that they're rational and they lie between -1 and 1. And then consider the set p plus q for all such q's. Now, p is a subset of p is a subset of 0, 1, and q is between -1 and 1. So p plus q is going to be a subset of -1 up to 2 for all q in here. Okay, that's straightforward. So the union is also going to be a subset of -1 and 2. Okay, but now we're going to use this fact that we've established earlier. So uh, take any element z in 0, 1. Take any element z in 0, 1. Then we have that there exists an x and p and a unique q, which we've deduced that is between -1 and 1 and is rational, such that x plus q is going to be z. So in fact, that means there exists a q again from here such that p plus q contains z. And what does this mean? This means that, I'm going to write this nicely, this means that the union is a superset of 0, 1, okay, is a superset of 0, 1, and it is a subset of -1 and 2. And now, okay, we've done a lot of work to show this, and uh, we assume that P is Lebesgue measurable. And since by adding Q to this set, so of course P plus Q should be interpreted as the set P plus Q where P is small p isn't big P. Okay, this should be interpreted as this, of course. And by adding Q, we've only basically translated this set, and translation doesn't affect the measure of a set. Just, when you have a set and you just move it along, that doesn't affect the measure of the set. And this can be shown quite easily. Okay, so um, we have this fact, and now let's see what the measure of this set is. So the rational numbers are countable, hence uh, the rational numbers are countable, hence we can do the following. So uh, okay, we then have the measure of 0, 1 is going to be smaller or than the measure of this union Q element, this P plus Q, and all of this is going to be smaller than the measure of -1 up to 2. Okay, we know how to calculate these two guys, so 1 is smaller or equal to the measure of uh, this union Q, P plus Q, smaller or equal to 3. Okay, now by using countable additivity, we can see that this is just the sum of all Q's rational and between -1 and 1, M P plus Q, smaller or equal than 3, which implies, because this is the same as just a measure of P, that 1 is smaller or equal to the sum between, well, not between, but over all Q's over MP. And now, is this possible? Is it possible for this to happen? In fact, it is not possible, and it is very easy to notice why. If MP is 0, then we have that the whole sum would be 0, and that would contradict the fact that the sum is bigger or equal than 1. So this cannot be the case. So MP is some quantity that's bigger than 0. But since the rational numbers are uncountable, well, not uncountable, they're infinite, so they're countable, but infinite, still infinite, and they're still infinite on the interval between -1 and 1. This would be an infinite sum over some positive quantity. So this would imply that the sum of MP is infinite. And that contradicts the fact that this sum is smaller than 3. And there's no other possibility for the measure of P. Hence, we can conclude that this is a contradiction, concluding that P is not measurable. So yeah, that's the proof. It's a bit involved. But I'm gonna just repeat the main strokes of the argument. So first, we found we defined what the set of all equivalence classes of that equivalence relation is, and then we found representatives for each equivalence class, and then we found representatives for each equivalence class such that they all lie within 0 and 1. And then we used some, sneaky tricks to show that the union of all all rational numbers, but between -1 and 1, p plus q, it covers 0 and 1, but is the subset of -1 and 2. So it covers 0, 1, but is a subset of -1 and 2. And since this is a disjoint and countable union, we can use countable additivity. And since translation doesn't affect the measure of a set, we finally can deduce that 1 is smaller than the measure of p, which is smaller than 3. And this is impossible. Well, no, sorry. The infinite sum is between 1 and 3, and this is impossible for an infinite sum, because if it's 0, it's going to contradict this. And if it's something positive, it's going to contradict this bound. And that's how we reach our contradiction. And we use the axiom of choice here and here when we choose our representatives for each equivalence class. And it's been shown that it's impossible to construct a non-Lebesgue measurable set without the use of the axiom of choice. So that's something to think about if you know about the axiom of choice. Okay, thank you everybody for watching, and I'll see you next time when I'll be going back to some Ramsey theory.